So John show you all the early history of CABDM until up to 2005, more or less, and I will continue from that and until nowadays with the state-of-the-art, let's say, simulation CBDM techniques. I will go through the methods that I'm using in my research, and then something about the modeling tips, and how to what to look at when you're modeling for an annual simulation, and then at the annual CBDM metrics at last. So starting with the methods, we saw how the four components method is working, and partially also how DaySim is working. So they are both using the rtrace command in radians, but still they have some difference between them. First, all these 5 methods are actually using radians, but they employ different technique with it. And starting from the two-phase method, rather than using rtrace, the simulation started to use RT-contrib, that was then renamed rcontrib when the simulation and the engine got more efficient for an annual simulation. I will call this method now two-phase method, because the rcontrib is rather more a command rather than a method on its own, and is still used in the 3-phase and 5-phase methods, but again they employ different strategy. So for now this will be the two-phase method. The 3-phase method then was introduced to account for complex fenestration systems. So like anything that redirect the light not in a more complex way than a clear glazing. This had some approximation, some assumption that make it quite a coarse method in somehow, especially for visualization. So it got refined with the 5-phase method afterwards, and this is, say, the latest technique that we're using. There was a further one introduced last summer, but that is called 4-phase method, but it's actually not that different from the 3 and 5-phase methods. This is just introduced when you have like a double facade or multiple more than one layer before actually getting the light into your room. Just for now, I will not talk about this, but just be careful not to confuse it with the 4-component method. And so the 4-component method and DaySim, they trace the rays with rtrace directly from the inside of the room towards the outside, and they treat the sky light and the sunlight in a different way, like John explained before. The main difference also between the two is that, well, DaySim use also a modified version of rtrace, to be exact, and it uses up to 65 points over the sun pass, depending on in which location you're doing the simulation. And while the 4-component method has those 2,000 or 5,000 points evenly spread around the sky vault. This has dramatically changed with the 2-phase method, so the first rcontrib. Here the sky definition completely changed. We don't have multiple sampling runs for each patch or each sky, but we simulate everything, all the sky vault and all patches, all at once. But it has there is an assumption that the all sky vault, sun and sky light, is treated in exactly the same way. So it's assigned a glow material, so it's a stochastically determined simulation, and the sky luminance is not at a point anymore, but it's spread over 3 patches, which are the nearest one to the sun location at that time. So this makes the sun not half an angle anymore, but a much more spread source of light. And one of the solutions was to refine the sky subdivision at this point, rather than using the classic Tregenza one and having these big solid angles for the sun. We now use a finer subdivision of this scheme. And this was called after Christoph Reinhardt, and the number on it indicates the number of division for each side of the patch. So if you have MF4, it means that you're actually dividing each side in 4, and you get 16 smaller patches in a Tregenza patch. So this was a way to represent the sun again as a small source of light, very intense. After this, the free-phase method came into the scene, and mainly because there was a need of simulating a complex fenestration system, CFS. These are called complex, but can be as simple as a Venetian blind. Just optically speaking, simulations, word speaking, they're fairly complex to simulate and to represent accurately. So this process divides the whole thing into 3 steps, separate, as the name suggests. So the first is sampling the interior part of our room with the ARC-on-trip simulation run. With this sampling, we are trying to find we are looking at the window surface for the interior. Then at that point, we apply a BSDF material on the window on the fenestration system, so that we have a correlation between the light flux that fall onto the window from the outside, so it's incident on the window, and the light that actually get transmitted into the space or get reflected off. And this is described in the BSDF that I'll show later. And the third step is from the outside surface of the window to then sample the sky again, so like find where the light comes from in a scheme that is the same as the two-phase method. So again, the patches and the sun apply to 3 of them. The BSDF are bidirectional scattering distribution function, and when we are talking about the Clem's angle basis, we are talking about a representation that is made out of, say, a matrix 135 times 145 that represent the correlation between each incident when the light is incident at each of these patches on one side of the window, then you get the corresponding distribution and quantity, like of the reflectance and of the transmittance in a window. So you get the distribution and the intensity. So these are using the free-phase method and are applied as a window materials. They are usually described in a XML format, so it's self-descriptive and contains even some information about the manufacturer and other things, and can be retrieved from a database, for example, the LBNL Windows 6 or 7, so that you can just download the description and the file in XML, or can be generated from Radiance itself. If you model your window geometry only, you can then use this tool GenBSDF to create this BSDF description for that specific system. And last, they can be built also from measure data if it happens that you have all the instrumentation needed to measure the light incident at every angle. And if you're using the description from the database from Windows 6 or 7, then what you get is always a Clem's angle basis, not a tensor tree, but you can use it also, exactly the same file, exactly the same description. You can use it also in a thermal simulation program. So it's good for when you're doing a whole building analysis. And wherever you find the BSDF material and the XML file, is a very good practice to check that, and if it all makes sense with a tool, for example, like this BSDF viewer that was developed at LBNL, and they show you on the left. You can select each of these patches as an incident light patch, and then corresponding to that, you get the distribution on the other side, so the transmitted one or the reflected one, and you can check how your system works and if that makes sense. So it's a very useful tool. And after the three-phase method, the five-phase method is a refinement of that, and it starts actually from the three-phase method output. So we are the situation we were before. We got our illuminance value and all the rest from the three-phase method simulation, but now we add two steps. So at first, we take out the direct sunlight, how we calculated it with the three-phase method, and then we re-added it, but using a more refined strategy, so that the diffuse light remains the same as the three-phase, but the direct component, which is the more delicate one, it's now more accurate and especially more realistic in images. So this is done by separating again the sky part from the sunlight part. So now we don't use anymore a sun that is just a part of the sky and is a glow material, but we use the over 5,000 points with a light source that are our little sun that we will choose depending on the actual sun location. And for the sky part, we still use the same component, the same results from the three-phase method as before, using a Tregenza subdivision or a finer one, but it doesn't matter too much. And another way to refine our results is substituting the Clem's basis BSDF with a tensor tree basis BSDF. So now we don't have anymore the light coming in and again coming out from a patch, so a big solid angle and being that smeared out inside the room. But we have if we have some specular reflection or some very intense and small light sources coming from the window, we can see those. And our system, our description, is refined only where needed. So, for example, this shows something like a slat blinds. So we get something diffuse at the top and a specular bit here. So this description is not a matrix anymore, but it's a variable resolution description. Here it's getting finer because it needs that, and here it's remaining coarse because it doesn't need that big accuracy. So in this way we are reaching a good accuracy, but without having too huge files and too overload on the computational expense. And yeah, to recap a little bit about the methods, we can look at the radiance parameter that we use at each of them. They are always dependent on the geometry that you're simulating. So these are not like strictly some recommendation taken as it is. But it's just to point out that while the four-component method and DASIM were using art trace, and so you're using radiance and setting it as you would do for an art trace calculation and for the standard ones. From the two-phase method onwards, the settings need to be changed in a few bits. First of all, the Monte Carlo simulation, the interpolation part is switched off. So whatever value you give to the ambient accuracy, ambient resolution, it will be overwritten as 0 because it needs to have that switched off in order to keep track of the origin and destination of the rays. So AA will always be 0. And to make up for this decrease somehow of accuracy in the results, we need much more rays sent around, so a much higher value for the ambient division. And that's true for all this method. And for the free-phase method, we also need 2 different sets of parameters for the view matrix inside the room or for the daylight matrix outside the room. So just, if you're using this, just remind that each method has its appropriate radiant setting. And talking about the complex fenestration system and how the different method handles BSDF materials, we still don't know how the 4-component method would work with that. And it was partially tested more for geometric description rather than BSDF. And they seem could implement BSDF in the future, but it's just rumor. I don't know. I'm not sure. And while the 2-phase method, it doesn't really simulate. It doesn't handle BSDF. It can simulate actually complex fenestration system if the geometry is accurate enough and if that's enough for the ray tracer. But the real method made on purpose for BSDF handling are the 3-phase and 5-phase methods. And you can find this different method also embedded in some software, some commercial software or even open source free software with a graphic interface. So for example, DaySim, I usually use it through Diva for Rhino, that is a plugin in a Grasshopper. Or the 3-phase method is embedded in OpenStudio, while the 5-phase is not yet, as far as I'm aware, is not yet in any interface, and the 4-component method, John has it if you want. And so if you want to know more about any of this stuff or try them yourself, it's Andy McNeil actually built most of this method, and he wrote very, very good tutorials. So those would be always a place to start if you want to have a go at any of these 5-phase method or GenBSDF. And now going into the modeling part, when you are actually doing some evaluation on some models that you've built or you received, there are some things to keep track of. And it's good to have a checklist at the beginning, but see that later. The model I'm using for the research and that I'm going to show also in the presentation are the model of these 4 classrooms. They're used by my research as a case studies, but mainly as a case study for another research carried out by my colleague Nafsika, who is at the back there, if you have a question. And she's monitoring these rooms with HDR captures during a long period of time, some months, every 10 minutes. And then she's also assessing the comfort of the student in this classroom, so trying to relate the user satisfaction with the luminance condition of this room. At the same time, I've simulated them, and while we'll be trying also to find some correlation between the 2 works, but for now I'm using them for intermodal comparison between the methods that I described. The rooms are fairly different between each other. They're all school, college classrooms, but they have different size. Some of them are side lit, or some of them are have double side glazed. and they are all looking towards different orientations. So they gave us a pretty good range of some classrooms as they are designed now or before in the UK.
Just in different locations, not the same building?
It's 2 locations. So 2 of them are in one building and 2 of them in another. And yeah. So whenever I start simulating any of these spaces, I always try to follow some checklist first, just to be sure that I don't have to rerun all the simulation again and again because I miss out something. And there are quite a few things to look at. So first on the geometry, if you import the model from anywhere else, from another software, it's good to check it, to double check that everything you were seeing in the previous software, you're still seeing it in the software that you're using at the end. And also, you should simplify it. So if you have tons of triangles and instead of a small curve or door handle or whatever, you should try to clean it up. And then it's good to add a ground plane outside of the building, even if some software have a tick to like add ground plane or something like that. Just is to be on the safe side, just insert also a geometrical physical ground plane. And then, yeah, it's the wall depth is important in lighting because we have a reveal that could bounce in a good fair amount of light. But some software don't show it, especially if they are all building simulation software. So for the energy part, it's not strictly needed. So they are not showing it to you, but they actually like OpenStudio adding it afterwards. So check in the manual or somewhere that is doing that. Then a check needs to be done on the input, some of the input parameter. First of all, the weather file, because it's climate-based daylight modeling is based on weather data. So it's good to check those, building a color map, something like this for the global horizontal illuminance and direct normal and so on. And maybe if you have both illuminance and irradiance, also to check on the efficacy, so that you can understand if the illuminance was measured directly or it was derived from the irradiance and things like that. This is a climate file for London. It looks very good. But for example, this is a climate file for a place in Canada, very high up north, and has a lot of infinite values here on the where the sun angles are low. So at sunset and sunrise, it just, I don't know, blow up something. And yeah, so you just delete those or be sure that the software handles those. Then if you have a schedule, especially for the matrix calculation, and you should check that too, if the total number of hours in a year that you're taking into account is the exact one. Even more if you are required to calculate sub-hourly data. So if your schedule is starting at 8:30, you should calculate 30 in a 30 time step, and some software don't do that. They have only hourly time step, for example. Then the sensor plane should have a boundary all around, because like John said, in the corner and creases, you need to make the parameters higher up to account for that. So if you leave a boundary, the calculation will be easier and will it will cut off all the excess, all the extreme values. And that has to do also with the grid spacing. So strictly speaking, it doesn't matter too much if you're using a 50 centimeters grid rather than 10 or 5, doesn't really matter. But the closest, the finer the grid, the closest you get to the actual boundary that you set. So that's has an influence on the results. And last, if you're using reflectance or transmittance that are not the standard one, it's good to report what you're using, because the values are are very sensitive. The results are very sensitive to those values. And then for some tools, the window surface normal should direct inwards into the room rather than outside. So also, yeah, check the window normal too. Once you've done all the check, you can run the simulation and wait for that much time, depending on the method. And so this is not a very fair comparison between simulation time for different methods, because for the 2 and 3, 5 and 5 phase method, it's all right. So they are for a room like this with 50 centimeters grid on my MacBook, they took 1 minute, 5 minutes, and 19, 20 minutes. The 4-component method took, for the same room, 24 minutes, but if you increase the accuracy of the grid, so you decrease the spacing, it's not going to take much longer, while the other simulation times are going to increase. And for DaySim, I had to use it from a window machine, so through Diva for Rhino. And so the specification of the machine were completely different. So rather than this could be a quarter of this, something like 12 minutes maybe. But it's not, too fair. And after all the simulation time, you get a lot of illuminance or luminance results. So you get a lot of data from all this, one for each sensor space and one for each time step, all together. But of course, we don't look at them like this. There are some more meaningful ways to represent them as a color maps, so of the illuminance that we get inside the room, or as a distribution on the working plane. Or another way is to calculate metrics out of them. So from all our annual results, we can do some post-processing, whatever software you want, and calculate the metrics. The one that we currently use are the UDI, DA, TAI sometimes, and ASC. So they've been inserted also in some guidelines and some green energy regulation lately. For example, the UDI and the DA are the required metrics in the PSBP for the new school here in the UK. And this was mandatory and launched by the Education Funding Agency. So it became all quite important as a method and a calculation. And then in the US, in the LEAD version 4 and in the IES NA recommendation, we've got the spatial daylight autonomy and the annual sunlight exposure. While the total annual illuminance is exposure used more for conservation work and artwork and museums. So if starting from the UDI, we can define it as an annual occurrence of illuminance being in certain ranges. The ranges can be whatever we want, basically. So we could even say that we can even describe it as too low, not quite enough, good, and too much. So depending on your need, on your type of building, on your task or requirement, you can set some ranges and see which part of the year fall into those. Same thing for the daylight autonomy. You set a threshold and see which part of the year you are over that threshold as a illuminance value into your room. The total annual illuminance is a cumulative value, so you just sum up all the values in a year. And the annual sunlight exposure is a bit more complicated because it has different dimensions to look at. So it's a portion of the room, so the portion of the working plane, in which you have direct sunlight with an intensity higher than a certain threshold for more than a certain number of hours. So you should when they made it, I think the purpose was to show when and where is too much light, direct light. And usually in the latest requirement, the threshold that we are using are 100, 300, and 3000 for the UDI. For the daylight autonomy, is over 300 or sometimes over 500. And for the annual sunlight exposure is direct sunlight over 1000 lux for more than 250 hours per year. Okay, so I use this matrix to express the results of the simulation, and I compare the simulation and the result expressed with this matrix for each of the methods I explained before. So this is a part of my research. I made this intermodal comparison. So for the four rooms that we've seen before, we've got the results expressed as a total annual illuminance, as daylight autonomy, and as a UDI supplementary and autonomous for the 5 method. And the agreement of this is very good, especially given that they use different techniques, as I said, but also different sky models, because the 4-component method is using the CIE blended sky, while the other method are using the Perez sky. And but still they match well with the appropriate parameter, of course. There is here an instance where the 4-component method is higher than the other ones, and this is a deep plan room, only side lit. So the 4-component method gather more light because it's kind of one bounce ahead of the others because of the direct skylight that is that has a light materials. But well, it's possible to double check this by rerunning those two. Okay, so in general for CBDR metrics, no matter really which method you use, on an annual scale, the peaks would kind of disappear in the statistical binning that you make. So all the excess will enter in the UDI exceeded or in the daylight autonomy, and the result will be leveled off. The same applies if we rotate those rooms that were before at their original orientation. If we rotate them all around the compass, the situation doesn't change. So again, we have higher values here for the 4-component method and all the others that agree pretty well. Now, if the only one that we haven't looked at is the annual sunlight exposure, and this needs a bit more effort at the beginning when you're modeling your rooms, because in the 4-component method and in DaySim, the direct sunlight calculation and the skylight calculation are already separate. So you get separate sets of value, and you look only at the direct sunlight. You take that and you do the post-process only on that. For the 2, 3, and 5-phase method, it's a bit more complicated because you don't have, well, you need some, or the software that is using it is doing something more under the hood. So the model is assigned a black material to switch off basically all the specular components of that you can simulate, and then you take only the direct normal contribution from the weather data. And then for the 3 and 5-phase method, there are in Andy's tutorial there are some guidelines on how to calculate only the direct component, because that's needed for the 5-phase method anyway. So these are the suggested ambient bounds and other geometry modification. The only one I'm not completely sure we need more study on it is the two-phase method, because there is nowhere is defined exactly how to get the direct sunlight component only. Anyway, after you do all this modification, you get some results from them, and these results are not really agreeing with each other at all. So for the annual sunlight exposure, it's because each method uses a different way of handling the sunlight part, then you get different results, very different. Like, okay, if it's northwest directed, you don't get any direct sunlight for that time and that value. But for example, for this room, we get a minimum of 6.5% for the four-component method and a maximum of 43 for the three-phase method. So given that it's requiring some regulation, this is, one has to be careful about this metric.
That's because that's diffusing the sky, the other methods, the 3, the 2, 3, 4,
Because it's
the initial ones are, no matter how much you divide the sky is still using a point, isn't it?
yes, because it's using a patch and smearing it. Yes.
Okay, so that's
Yeah, and so same thing. If you rotate the building all around, very different results all the way. And I leave you with this, and then I will ask you a favor in a week or a few weeks. I'm running a survey that I haven't launched yet, but just for anyone that has used CBDM or is using it now to understand how you're using it and which kind of metrics you use and which is the purpose of all that and so on. So David will contact you and send the link around. So if you want to give a contribution to this, thanks a lot. Thanks.
You're clearly using a number of software for the various methods, if I understand. For the modeling, what are you using?
For the modeling, all right. I've used mainly SketchUp, and I remodeled them all in SketchUp. I used at first Rhino,
Okay.
but
I was wondering how much tweaking is then required for going from Diva to then going to Ladybug and Honeybee if you're using them.
oh no, that's
So the model is still
is exactly
solid.
the same because they're all plug-in in Rhino,
Okay.
so they're all working on the model that you built in Rhino.
So you don't lose or you don't risk having to.
No,
insert the model.
that's working straight on there. Even though, anyway, the model is translated into radians description. So if you really want to check it's producing a radians file, and you can check that too.
Okay, so anyway, it's SketchUp and then Rhino.
Or Rhino directly, yeah.
Have you really encountered any problems with the way DaySim interpolates the weather file, which you use from any source, because that's something I've experienced. And when it does its time step, it interprets the weather file in its own way, and I've experienced some problems there. Have you had that?
I didn't have problem exactly, but I know that it's using a stochastic interpolation, so not linear. So it's giving a randomness to the intermediate steps.
Yeah, because it's not strictly interpolation with just as soon as you, and it doesn't really. I don't think does it report that it's doing it, or does it just do it automatically? If you just say.
Files, I think it does report that weather step as well. It does report
Okay.
it.
Because if you went down to sort of 5 minutes, you could see it was sort of like that now. That was pretty much an add-on, and I went for straightforward interpolation and would recommend that rather than having this stochastic model which is adding something you don't quite know what
Exactly.
under the hood. So
That was it. Yeah. Okay, that's good.
Question about the sort of dodginess of the sunlight power. Did you compare to the standard radiance like an hour by, I mean, what was the correct answer? Do you know which one is the correct one, or they are all, you don't know?
No, I didn't compare with hour by hour radiance. Yeah.
Because it
I
shouldn't
can-
take too long. I mean, it's direct, so it should be.
Yeah,
Yeah.
it
yeah,
should be
yeah.
before, like, tuck.
I mean, the full component is just doing essentially just like the standard radiance thing. If there was something wrong in that part of the full component, it would have shown up in the validation.
But that's also for the others. I mean, because the global annual indexes are the same. That may mean that the indexes are not representative much of reality because it doesn't matter what happens. They're always the same number, or that all the methods are wrong.
I think it's just incredibly sensitive to even the smallest amount of smearing.
It's,
And there's a huge amount of smearing that goes on,
yeah.
when using straightforward clems, and it's kind of there's still smearing intensity, but it's less.
But the three-step method has as well a description of the sun, which is fairly dense, as you have. So I don't think that should change.
No,
much.
but the free phase is then using the 5-phase.
Yeah.
Yeah.
I mean, if it is just a simple window and you're not using a complex matrix, it shouldn't be that different. I'm a bit surprised. I would have actually checked hour by hour because it's really fast.
Yeah.
You can do
Yeah,
that.
yeah,
You don't know
sure.
Which one is the strange one?
Yeah, of
Yeah.
course. Can do that.
I mean, these results have just dropped, came out, just been done recently, so they'll be looked at for sure. Yeah.
Did you try them with AB0? Was there any difference, or the difference between the four-component method and three-phase method was comparatively less in that case? Do you compare that with for the
yeah,
annual sunlight exposure?
Yeah, it was like setting AB0. It was because with the annual sunlight exposure, you're looking at the direct sunlight only. So it's
No,
It's
but
set.
in the table you're saying that for the two-phase, three-phase, and five-phase.
to look at the zero.
Yeah.
But then you have a glow material sky, right? So
That wouldn't work. Or?
with the two-phase method, it wasn't finding the sun anymore.
John, in the benefits of working as a designer as a D&B or D&B contractor, what do you think is the reason that we're getting so wide a result differences? Because I am seeing simulations not only from ourselves but from other practices as well, which lead us to think that the actual physical dimensions of the rooms, which are what the contractor tends to be interested in, things like floor to ceiling heights, and minimising those and maximising this to meet the the educational funding agency's requirements, are doing something that what you've shown to me today is that the methodologies between the softwares seem to be very good.
Remarkably good, actually.
As that, and I am now not so worried about that, but I'm still seeing, either as a peer reviewer or as a designer or commissioning simulations myself, a lot of difference in the results, which turn out to be differences in money to our clients as contractors.
Oh, well, it's not just the method, but the person doing it, of course. That's a variable. There are some techniques which produced climate-based metrics, which we haven't shown here, and some of this is commercial software, and from preliminary sort of testing, they did show some deviation from what we've got. I mean, we won't name the software. It's just we say it's in beta. I think that they're still considered beta versions, but is it possible that these are actually being used?
Well,
I
I'm
don't
not sure.
know.
I'm not sure, but what we get from our contractors is that they've had a different result and a different design for classroom dimensions, which is where the money actually is in this. And they don't need brise-soleil on the southern facade, and they are doing lowest common denominator design to win the projects. That we are being driven to solutions that we as professionals would not necessarily want to go to.
Yeah. Perhaps there's a good case for somebody, maybe the EFA, publishing a set of benchmark results, making the models available, and perhaps suggesting to people that they should benchmark their techniques against those results.
I've talked to Richard about that kind of philosophy as well, and that maybe material scripts ought to be given out so that all the designers in that field use the same way, and we can get an apples to apples comparison between this, because commercially contractors are losing jobs because of that, design teams are losing work, and it has to be a fair playing field.
Sure. I mean, for anyone that's done any intermodal comparison with thermal models, I imagine they were surprised at the level of agreement there, because I don't think you'd get anything like that if you compare the whole raft of generally used and accepted thermal models. You get significant variation.
Absolutely, I accept there has to be some variation. It's the fact that some of our clients don't accept that, either as the contractors or as the EFA's regional areas, that this is right. They think it should be an ultimate number every time.
Yeah. Yeah, but point well made. Yeah.
I would suggest that one of the reasons that the thermal models are different is the interpretation of the material values. I think it's clearer that there are a simpler range of material values in lighting simulation. And you made it simpler by having one person do those simulations, so keeping that consistent. It's entirely feasible, given the importance of the reflectivities. If you haven't got, and I don't know the system you're using, if you haven't got a specification that says you must use this for the glazing material, you must use this for the assumed values of the roof, wall and floor inside, or even for the furniture, if you have to do that, then you will have hugely different predictions of the light levels, particularly towards the rear of the room.
Eleonora is looking at the sensitivity of input parameters to output results.
He was in India.
Yeah, you saw that, of course. You saw that,
I just say this is particularly interesting when you look at some of the new materials which are out there. I'm thinking particularly of some of these very highly reflective paints, where people like Dulux are claiming 95% reflectance from them, and contractors are saying, well, why haven't you put 95% reflectance into your model?
Well, yes, maybe on the ceiling, but anywhere else. Perhaps just follow on, Mike. Perhaps I'd add that a thermal simulation, even though it's a much more mature discipline than lighting simulation, certainly climate-based lighting simulation, it's actually much more complex. You've got thermal inertia, and you can have things happen in a thermal simulation, like a little leak somewhere can have a huge impact on the results. Whereas a lighting simulation, it's not dynamic, it's strictly a sequence of static simulations. There's no thermal lag or inertia effects, and you don't have any of these unpredictable energy flows which you do with thermal. As long as you do a good job with your simulation parameters, light shouldn't be appearing in strange places, unpredictable. But with energy, of course, that can happen. Slightly wrong input specification or coefficient of resistance or something, and you get very different results.
Can I just ask one last question? Where in this workflow does the G value of the glass play a role?
But it doesn't, because it's a it's a total energy, and we've just been looking at visible
Light.
visible light.
But when because we're only relating it to the sky luminance. The solar energy is only affecting the sky luminance.
It's the visible part of it.
Yeah,
Yeah,
so that's why it's
the luminance. Even though radiance is called radiance because it predicts
Yeah.
radiance, we always just use shortwave model for reflectance and transmission values.
Can I ask one? Made a suggestion. I haven't asked a question, if I may. Can I summarise Eleonora's presentation for myself a moment? So long as I'm not trying to do what I've always had difficulty understanding in the IES North American documentation, the annual sunlight exposure measure of potential for glare, that in fact the simplest method that I can use, and therefore the fastest, is going to produce as reliable a result as the more complex method.
If you do it well, that would
Yes.
be, yes, that would be.
So long as I'm not trying to put in BSDFs and all sorts of modelling complex fenestration, which
yeah, all-
the simpler methods don't allow the possibility.
All the comparison was done for clear glazing
Yes.
anyway, so yeah. That's
Okay, if you can bear with me just for a few seconds. Firstly, I hope you all found that as interesting as I did, and I wonder if you could share with me showing your appreciation in a normal manner.